Hi, this is Big History 2020, presentation number 7. We have been talking about Big Bang, and this is a evidence-based course, so we will look at what are the evidence that Big Bang is the correct theory. So far, we have looked at the expansion of the universe. This is concluded by looking at the redshift of the spectrum we collected from different stars and galaxies. We have also looked at the cosmic wave, microwave background, which we will go into more detail later. So we still have another issue here. We talk about that in the initial universe, the universe is very simple. Most of the elements that is formed during the nuclear synthesis stage is hydrogen, helium, and lithium. So can we verify that? So we can look at the abundance of these light elements, hydrogen, helium, and lithium. As we have talked about, the Big Bang Theory predicts that the early universe was a very hot place. About 1 second after the Big Bang, the temperature of the universe was roughly about 10 billion degrees, and is filled with a sea of neutrons, protons, electrons, anti-electrons, photons, neutrinos, and so forth. These are the exhausted particles which exist today, which is our normal matter. As the universe cooled, the neutrons either decay into protons and electrons or combine with the protons to make a deuterium, which is an isotope of hydrogen. During the first few minutes of the universe, most of the deuterium combine to make helium. There will be a small trace of lithium. Lithium consists of 3 protons and 4 neutrons. They can combine to produce these kind of elements. So we would want to look at, well, if this is the case, what is the ratio among them? How can we determine what is the correct ratio? So we have a graph here. This is a prediction based on what we know about the behavior. This particular graph is in a log graph. That means every unit is 10 times more or less. So it's not a linear scale. It is a log scale. Using this, we can predict whether our universe is actually correct or not. So helium itself is quite stable, depending on the initial density of ordinary matter relative to photons. We know the photon's energy, and therefore using Einstein's equation, we can calculate the photon's mass, energy equal to mc squared. And then we have the ordinary matter. We know the ordinary matter's average density. Therefore, we will have this vertical line, the vertical red line. From the vertical red line, we know this is what we observed. If the universe did have Big Bang and the nuclear synthesis do occur, then it should produce the different elements at the intersection, represented by circles here. So we will have mostly hydrogen, because hydrogen is a single proton, so it captures an electron and remain there. So most of them would be hydrogen. Then helium is much more stable than deuterium, and therefore we will expect to have more helium. Deuterium a little bit less, and then we have another helium-3, which is less stable than helium-4. So this is the ratio of what we would expect under different conditions of the density of proton, relative density of proton and matter. This result shows that of the about 24% of the matter produced will be helium, as predicted here. So what about the red line? Is that a possible way of verifying that's the red line? Yes, we have a satellite which is able to directly measure the ordinary matter density and find the values to be about 4.6%, indicated by the vertical line here, and it leads to the predicted abundance as shown by the circles in the graph, which is in good agreement with our observed abundances. So basically now the Big Bang Theory has at least three very strong evidence. The expansion itself, the ratio of hydrogen, helium, etc. in the universe, not necessarily on Earth here. We are talking about in the universe. We will talk about that maybe much later, about how we can actually measure the ratio of hydrogen, helium, etc. in the universe. But anyway, that will be another topic later. Then we also have the microwave background, cosmic microwave background. So we have all this. Now, with all this, we would like to ask, the initial universe is so isotopic. It's almost like a flat surface. How come the universe today is so different from the early universe? So what are the mechanisms that our present day universe has developed to the present day universe? What are the mechanisms there bring the initial universe to what we see? In order to understand that, we have to look at the so-called formational structures, how we understand the structure of universe at the moment. Until recently, we don't know the answer to that one. But since the microwave background radiation, we were able to have a bit more understanding. So let's review this cosmic microwave background. This cosmic microwave background, as described, we have the cooler spots represented by the blue. We have the hotter spot represented by the red. And the difference is very small. The difference is about 0.0002 degrees Kelvin or C there. They're basically the same. So a very minor difference. But still, we see that very small difference. And this is this very small difference that lead to today's structure. So we need to understand why this why the universe will have this, although small but still significant difference. How this difference come from? So this slide actually talk about the temperature difference. So we are looking at the fluctuations of this cosmic microwave background. Small but important. So where did these slight variations come from? To explain that, we have to go back to the very beginning in the inflationary epilogue. At this stage, the universe was expanding very, very fast. It is a very fast exponential expansion. We know that it will expand a factor of 10 to the power 26 from a very tiny universe into a universe of about 10 centimeters. During this period, several things happened. First of all, using the Heisenberg's uncertainty principle, we know that there will be a certain quantum thermal fluctuations. There will be slight variations because the matter there is in discrete units, small particles. Although it is mainly energy, still there's a small fluctuation. These small fluctuations during the expansion inflation period, it will expand, and therefore the small fluctuation is now being diluted to smooth out, but still it's there. So there's one type. In order to predict that, we can use some mathematics. The usual mathematics is using something called scale invariant Gaussian field. Without going into mathematical details, okay, Gaussian random field require two parameters to describe the field. One is the amplitude of the waves in the field. Now, Gaussian random field basically is a mathematical formula describing a field, that means a space. In a space, there's a lot of different waves, and these waves have two things. One is the frequency itself, that's the spectrum. Another one is the amplitude, the size of the wave. The larger amplitude means the wave is bigger, and the higher frequency means the spectrum is more closely together. So one is this tensor to scalar ratio, which basically describe the frequencies in the random wave field. The other is, of course, the amplitude, which is indicated here. So there are two parameters. One is the amplitude of the spectrum, and the other, or call it the spectral index. Another one is the tensor to scalar ratio. Why is tensor? Tensor is a differentiation description of multidimensional differentiations. So these multidimensional differentiations compare with the scalar compared to a constant. With that ratio will describe how varying the field is, and that's basically we are describing how frequent the field's difference or the frequencies. So using the mathematics, we can do some prediction. So applying this Gaussian random field onto the inflation model, we will expect the two specifying constant, one to be between 0.952 to 0.98. That is the spectral index. The other one is tensor to scale ratio, should be about 0.1, nearly 0.1. So again, with the prediction here, what we need to do is verify that this is actually the case. So there is an experiment called operated by the European Space Agency, working between 2009 to 2013, trying to map out how different part of the cosmic microwave background is with all the frequencies, in particular the infrared region. It found that the spectral index is about 0.968, which is right in the middle of the range that is predicted. And then the tensor scalar ratio is less than 0.11. That means it is very close to 0.1 as well. So again, by looking at the variations in the current known cosmic microwave background and looking at the waves, wave, something like for example, we have we are on traveling on an ocean. Okay, we see the ocean waves. These ocean waves is formed by some physical constraints. So this spectral index and tensor to scale ratio describe these waves we see in an ocean. This ratio, these two numbers, depends on, in the case of an ocean, depends on the water, the density of the water, the properties of the water. So similarly, in the universe, we can use that to estimate whether the variations, the waves on the cosmic wave background is the same as described by the quantity that we can describe to it. So this is basically the idea. As these variations being inflated and expanded, so the fluctuation becomes everywhere in the universe, but it's becoming smaller and smaller. So that is the one reason. The other source of variation is something called the surface of the last scattering. Suppose we have a balloon. Inside the balloon, we fill with some liquid. So we close up the balloon with some liquid. Then if you, for example, you pinch on the balloon, then you will see a wave propagating all around the balloon on the surface. Now that is the variations coming from the surface. If we think of this like that, then the universe at the time when it becomes transparent, the same thing. It is like a bounded balloon with water in it. The balloon surface will have some ripples, and these ripples should be apparent from later when it becomes transparent. Our image, the cosmic microwave background, should have an image of this. So there are two sources of variations. The first source of variation, just recap, is the quantum thermal fluctuations when the universe was a very small object. The second is when it's expanding. During the expansion, there will be waves inside in the universe, and that will cause a variations, as well as the surface itself. The universe, the surface, the outer bound will also have a wave, and that is called the surface is called the last scattering surface. Now, for our example, the balloon, the thickness of the balloon seems to be quite small. So the question here is also whether the scattering at that surface, how thick is that surface? So there are two issues here, and again we can do that using what we know from the cosmic microwave background. And in terms of determining that, there are two effects working on each other. One is the acoustic oscillation. Acoustic oscillation basically means the surface itself, the material is oscillating. Why it's called acoustic? Because we know that, for example, we hear something. It is because the air between my mouth and your ear consists of air particles, and my sound wave travels through the particles and causing my sound wave travel through the air, causing the air particles to vibrate at the frequency of my sound. And when it reaches your ears, it will push your eardrums and move, have a small vibrations in your ear canal, and therefore you can hear the sound. So when we talk about this acoustic oscillation, we are talking about the matter that is in the universe that is oscillating, and the wave that is traveling in this matter. So that's the acoustic oscillation. And there's another is the diffusion damping. That means when I'm talking, the sound wave travels out, but it will eventually get less loud. And there are two reasons there. One is the spherical spread of energy. The other is the damping. The air molecules will hit on each other and slow down the vibration. So we understand that, okay, in the universe, the same thing should happen. Now, as we have said before, the whole concept of understanding our universe is based on the assumption that physics laws are the same no matter at what time. So what we observe today, the physics or the chemistry or the biology, what we observe today should apply. All the scientific understanding we can learn today from our today's world should apply at the beginning of the universe until now. That is the basic assumption of scientific investigation. And therefore, when I'm talking about the cosmic microwave backgrounds variations, and and isotopies, we are thinking of, okay, this universe is a matter, a ball of matter, or something. Of course, we can't say it's ball because we don't know the outer surface of the universe. But anyway, we think of it as a ball, as a ball with matter there. We know that there will be acoustic oscillations. We will know that there will be damping effects. We know that all these things we can learn from the daily life physics here, and then apply to the conditions that we know about the universe at the very beginning, and apply that and use that to draw out observations which we can verify or we can falsify. So going back to these acoustic oscillations, it is basically caused by, now if we want to have an oxidation, we need a two force, one pushing in one direction and another pushing in the other direction. When we have two forces pushing in different directions, then they would cause a vibrations, and that is where the oscillation comes from. So we need to know where are the sources of these vibrations. The first source is, of course, the pressure of the photons hitting on all the barons, all the charged particles. The charged particles is a matter. When light hit on it, it will absorb or give some energy to the light, and therefore it will move. So this is the one pressure, the pressure from the light hitting on all this material. And the second is, these materials are mass, and therefore they will attract each other under gravitational attraction. So one force is pushing them away by the light pushing all these particles away. But at the same time, the particles are being attracted to each other by gravitational force. So there are two forces here. These two forces will cause an oscillation, and that is the result of this oscillation. And when light no longer can interact with the particles, that means the universe becomes transparent, then the light pressure is gone, and therefore there will not be any more oscillations. And therefore the oscillations will finish when the universe becomes transparent. In order to calculate that one, then we have two types. Again, we are not going into the details of this highly specialized physics. One is called adiabatic density perturbations. This is the one which is correct. Meaning the adiabatic density perturbation means energy is conserved. Basically, the photon energy hitting on a charged particles is equal to the initial energies of the photons and the particles. The final energy of the photon and the charged particle is the same as the initial one. So that's basically called the adiabatic density perturbations. We can use that assumptions and then work out what is the result, what will be the frequency, what will be the amplitude, and so forth. The other effect is a damping. Damping is caused by the mean free path of photons. That means when the photon travel from one heat to the next heat, it collide with a charged particles, and then it will bounce back and then hit another particles. The mean distance is called the mean free path. The mean free path will be important at the last moment when we see the cosmic microwave background. Before the universe becomes transparent, this mean free path keep on bouncing on each other. We don't know how it bounces. We have no data. But at the moment when the universe becomes transparent, that means photons is getting less and less able to be bounced back, because all these charged particles, the nucleus started to capture the electrons, and after it's captured the electrons, it becomes neutral, and becomes neutral, it will not bounce the photon again. So basically, this is about the depth of the last scattering surface. Now again, we are thinking of it like a balloon, at the balloon surface, the last surface before the balloon bursts. How thick is that balloon? Of course, this is just a simplified model, because we know that the universe consists of everything. We don't have the edge, but we still can apply the same idea and talk about this last scattering surface. The last scattering surface can be calculated or measured. So again, there are experiments trying to measure this. Again, we are not going into details, talking about the probability and so forth. And eventually, we figure out that it took about 115,000 years for all the electrons to be captured by the nucleus. That means the process of being not transparent to becoming transparent take place over roughly 115,000 years. So it's not a very fast process. From when the temperature started drop to the point that electrons are able to stay with the nucleus, then we started to form atoms. But that take time for all the electrons to be captured by the nucleus. So roughly, it started at 372 years after Big Bang, and it took about 115,000 years to finish it. So what we see, the cosmic microwave background, should be roughly 487 years old universe. That's what we know today. Thank you for listening, and I know this is a particular difficult lecture, but I would like you to get the idea that all the work the scientists have been doing is to try to verify the theory by looking at different aspects of the theory and see whether we can try to measure some of these consequences if the theory is correct. And if we can verify that, or if we can falsify it, that means the theory is wrong. So far, this Big Bang theory of the beginning of the universe seems to hold very well. So we are not going to talk about Big Bang from here onwards. We will be looking at how these find very minute differences in the cosmic microwave background lead to today's universe. What that little difference means in order to produce the universe of today. That will be next week. Thank you very much.